Hi there, welcome back. Let's discuss section 24, a hypothesis test for the mean. We'll consider the following example. A coffee machine dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample of 20 cups. We'd like to know, is there evidence that the machine is shortchanging customers? We're going to follow the same 6-step process that we did for a hypothesis test for a proportion. Step 1 is to describe the parameter of interest. Here it is the mean amount of coffee dispensed by this machine. Step 2 is to state two competing claims about the parameter of interest. So we'll start by stating the null hypothesis, which we denote by H naught. And this asserts that the coffee machine is doing what it's supposed to, that on average it's dispensing 10 ounces of coffee per cup. So the null hypothesis is that mu is equal to 10. The alternative hypothesis we denote by H sub A, and this is the assertion that the coffee machine is shortchanging customers. That is, mu is less than 10. Step 3 is to check the appropriate conditions for a hypothesis test. It turns out these are the same assumptions and conditions we needed to check for the one sample t interval, otherwise known as the confidence interval for a mean. So let's start with the randomization condition. Here we were told we had a random sample of 20 cups, and in all but rare cases, the sample size will be less than 10% of the population size. And here 20 is certainly less than 10% of all cups. The other condition to check is the nearly normal condition. And for this, you always start by sketching a histogram of the sample data. So you can see I've got a rough sketch here of the histogram of the sample data. It looks roughly unimodal and symmetric, so it's reasonable to believe that the amount of coffee in all possible cups could be described by a normal model. Step 4 is to calculate a test statistic. Let's start by jotting down some important information. N, the sample size is 20, which means the degrees of freedom is 1 less than that, 20 minus 1 or 19. And then I've used technology to calculate the sample mean for me. Y bar ends up being 9.845, and I used technology to calculate the sample standard deviation, 0.199. With that, we can calculate the standard error of Y bar. It's given by S over the square root of N. So in this case, 0.199 over the square root of 20, which is roughly 0.0445. Now we'll calculate the t statistic, and it's just a standardized value like z. We end up taking the sample mean, y bar, subtracting the hypothesized mean, mu naught, so remember this is coming from the null hypothesis, and then dividing by the standard error. So here's what that looks like. Y bar is 9.845, the hypothesized mean was 10, and the standard error is 0.0445, giving us a t-statistic of negative 3.48. And what this says is our observed mean, y bar, is 3.48 standard errors below the hypothesized mean. Step 5 is to calculate the p-value. And you see here I've sketched the t-distribution curve corresponding to 19 degrees of freedom. So I've labeled it t sub 19. It resembles the standard normal curve. Notice it's centered at 0 and is bell-shaped, but the tails are a little bit wider than the standard normal curve. So I've labeled our t statistic negative 3.48. I want to know the area under the curve to the left of this. That area is our p-value, and we can use technology to calculate this for us. We have what's called a t probability calculator. I've got a link to this in our Canvas page. So I'll switch over to that applet. Looks like this. Notice I've entered 19 for the degrees of freedom. This vertical blue line corresponds to our t-value, negative 3.48. We want the area under the curve to the left of this, so I'll check the box for less than, enter our t-value, negative 3.48, and it gives us that area, 0.0013. So our p-value is 0.0013. We'll use that in the next step. The final step, step 6, is to make a test decision based on our p-value. Our p-value is very small, 0.0013, so we reject the null hypothesis. There is strong evidence that the mean amount of coffee dispensed by this machine is less than the stated 10 fluid ounces. Now, it's always good to include a confidence interval with your hypothesis test. We've rejected the null hypothesis, but that doesn't tell us what the mean value should be. So that's why we're going to include this confidence interval, which we set up like this. We saw this in the last video. The sample mean, y bar, plus or minus your critical value, t star, and I've included the subscript 19 for the 19 degrees of freedom, times the standard error of y bar. So y bar is 9.845. I'll talk about how we find this critical value in a moment. And by the way, we want to construct a 95% confidence interval here. And then we'll multiply by the standard error. So let me switch to the t-table to show you how to find this critical value t star. Here's the t-table from the back of your book. As I said, we want to construct a 95% confidence interval. So I'll first go down to the row corresponding to 19 degrees of freedom, and then we'll go over to this entry here, 2.093, which is in this column labeled 0.05 and 0.025. What the 0.05 is the area between the two tails, and then half of that area, 0.025, is in the one tail here. So because we're doing a 95% confidence interval, there should be an area of 0.05 between the two tails. Using that critical value from the t-table, 2.093, we can finish our calculation and we see that the 95% confidence interval is 9.75 to 9.94. So we are 95% confident that the machine dispenses an average of between 9.75 and 9.94 fluid ounces of coffee per cup. That wraps up our discussion of a hypothesis test for the mean. I'll see you next time.